In these problems, we are using something called the second derivative test to look at a function at one of its critical numbers. And just as a reminder, where are critical numbers on a function? Well, it's where the slope of the tangent line is 0, and that might be a local max or a local min, or it's where the function itself is undefined. Those are types of critical numbers in a function. So what we're going to do is we're going to find where those critical numbers exist, and or where one of them does, and then we're going to use the second derivative test to decide, is this a local maximum? Is it a local minimum? Is it something else? And the second derivative test is pretty easy. If you have the second derivative, you just evaluate it at that point. And if it's positive, it means it's concave up. So if it's concave up at this point, it would be a local minimum. If it's concave down, it's going to be a local maximum. So that's the basic idea. And luckily, they've done a lot of the work for us here. So we've got this function, 12x to the 1/3 plus 2x squared, and they've taken the first derivative for us. So that's nice of them. We got 4x to the negative 2/3 plus 4x. And then they've taken the second derivative. They've even given us optional ways to write it. I mean, this is just manipulated a little bit algebraically. Maybe it makes it easier for some reason, or maybe not. The key thing to look out for here is if you have negative exponents, you need to realize that it's possible the x is on the bottom of a fraction. You don't want to just plug in 0 for x and say 0 to the negative 2/3 power is 0, because it's not. It's going to cause this to be undefined. So I would say, when in doubt, rewrite this. 4x to the negative 2/3 is 4 times the cube root of x squared. That you can see, and I'll put the rest of the function there, that you can see is going to be a problem if we put 0 in it. So be alert for that. And in this first one, they're giving us 0 as the number that we want to examine. So it says in the parts below, use the above information to analyze the behavior of the function at the critical number 0. So first it says, why is 0 a critical number of the function? Well, this is my rewriting of the first derivative up here, and you can see it's not defined there. Is it on the function itself? Well, yeah, you could put a 0 in here, and what you'd get is 0. So this point is at the point 0, 0 on the function. So it's on the function, but it's not. Its derivative is not defined. The way that happens is when you have a function that goes vertical for a while, perfectly up and down. And that point, the first derivative is not going to exist, or it's going to be undefined, but the function itself could still be continuous. So why is 0 a critical number of the function? 0 is in the domain, but f prime of 0 does not exist. Okay, we don't have a slope for that. It's undefined. All right, what can you say about the tangent line to the curve? Well, in this particular case, when the point is on the function, but you can't compute a slope for the tangent line, that means it's vertical. So we can say the tangent line is vertical. Your other choices here are that the tangent line is horizontal. That would be the case if the first derivative was 0, or the tangent line cannot be uniquely defined or does not exist. That might happen if the function itself is undefined there. I don't know how this could possibly be a critical number, but I guess I won't worry about that. All right, C says find f double prime of 0, give an exact answer, and use the does not exist button as needed. So you can see here we also have x on the bottom of a fraction. So this is also going to be not defined. So the second derivative also does not exist at that point. So we will just use that does not exist button. All right, then it finally says, using your previous answers, can you apply the second derivative test for f? And we can't. You have to have a second derivative to tell whether it's positive or negative. So it cannot be applied. Let's try one more where we actually can apply the second derivative test. So here we've got a function 24 times x minus 5 to the 1/3 minus 4 times x minus 5 squared. And they've given us the first derivative and the second derivative. And you might think, oh, whoops, look, we've got negative exponents, so we better be careful about x being on the bottom of a function. In, in this case, we only have to worry about that if we're evaluating it at 5, because that would put 0 on the bottom of a fraction. In this case, we're evaluating it at 6. So Let's find the first derivative at 6. So 6 minus 5 is 1, so this would be 8 to the negative 2/3. Sorry, 8 over 1 to the negative 2/3, and 1 to the negative 2, well, sorry, 1 to the 2/3. 1 to the 2/3 is just going to be 1, so the first part is 8. And the second part, 6 minus 5, is 1 times 8, so it's 8 minus 8. It's 0. So our first derivative at 6 is 0. Next, it says, what can you say about the tangent line? Well, if the first derivative of 0 is 0, then the tangent has a slope of 0, and that means the line is horizontal. Now it says find the second derivative of f at 6. So let's try to calculate this. We're going to plug a 6 in again. We've got 6 minus 5 is 1. That's on the bottom of the fraction. To the negative 5/3 power is still going to be 1. So we've got 1 on the bottom of the fraction. And then we've got negative 16 and 3. So this is just negative 16/3. Minus 8, which I'm going to write as 24/3. So that is negative 40/3. So that's our value for the second derivative. If the second derivative is negative, that means the curve is concave down, and we are at a local maximum. So that's what we're going to choose in this last part of the problem. The second derivative test can be applied. We've got a second derivative, and at 6, it's a local maximum. So that is a little bit of work with applying the second derivative test.